Every once in a while, a scientific paper comes along that doesn't just push the boundaries, it feels like it's questioning the very fabric of reality. Today, we're diving into the Garcia experiment, a totally wild look at what might happen when you engineer the world at the atomic level and start to literally squeeze reality itself. So, the whole thing really boils down to this one kind of mind bending question. We've got a pretty good handle on how energy works out in the open. But what happens when you cram it into a container that's so tiny, so perfectly designed, that the normal rules of physics just start to bend? That's exactly what these researchers went after. And this gives you a feeling for the incredible machine they had to build to even ask that question. I mean, this isn't just theory on a blackboard. This is real, hands-on, atom-by-atom engineering. What you're looking at is basically a system designed to sculpt energy, creating conditions in a lab that honestly used to be pure science fiction. So their whole goal is to explore this new frontier at the nanoscale. It's the place where three fundamental things crash into each other. You've got physical matter, you've got focused energy, and then you have the quantum vacuum. And that last one is the real kicker. What is empty space, really? And what happens when you start building walls inside of it? Okay, so how do you even build something like this? Well, the researchers needed a very specific set of tools. It's almost like a recipe, really, with three absolutely essential ingredients. Let's break them down one by one, because how they all fit together, that's the magic here. The first ingredient is the sensor, a nitrogen vacancy center, or NV center for short. And this part is just wild. You take a nearly perfect diamond, you knock out one carbon atom and stick a nitrogen atom in its place, and then you leave the spot right next to it empty. This tiny, perfect mistake creates a quantum system that's unbelievably sensitive. It's like the most perfect needle on a record player, able to feel the absolute tiniest changes in the world around it. And this is what it actually looks like on an atomic scale. That yellow sphere, that's the nitrogen. The V is marking that empty spot, the vacancy. It's this exact setup, locked inside that super rigid diamond structure, that makes it the perfect quantum probe for the job. Okay, ingredient number two, this is the stage where all the action happens. It's called a fractal metasurface. Now, the name sounds complicated, but the idea behind it is actually beautiful. A fractal is just a pattern that keeps repeating itself at smaller and smaller sizes. And when you etch that pattern onto a surface, you've basically built a whole set of nested antennas, all working together for one purpose: to snatch energy out of the air and funnel it down into impossibly small, intense hotspots. And yeah, you can see that pattern right here. See how the basic cross shape is repeated inside itself over and over again? The paper calls for a multi-level fractal design, and that complexity isn't just for show. Each one of those smaller layers is better at capturing and concentrating the energy. And for our final ingredient, we need the energy itself, terahertz waves. If you look at the electromagnetic spectrum, they're right there in the gap between microwaves and infrared light. For our experiment, you can just think of this as the drive. It's the blast of energy they pump into the system to get everything started. All right, so we've got our super sensitive probe, we've got our fractal antenna, and we've got our energy source. Now let's see how they put it all together in the lab to create what you could almost call an anomaly engine, a machine built for the sole purpose of studying physics at the absolute bleeding edge of our understanding. Oh, I love this slide, because on the left you've got the neat, tidy little schematic of the sensor, and on the right, the glorious, complicated, messy reality of the actual lab equipment it takes to make it all work. It's just a perfect picture of how much incredible engineering it takes to ask these really fundamental questions. Okay, so let's boil this all down. This is the core of the experiment right here. You take that fractal surface, you hit it with terahertz waves. Those fractal antennas grab that energy and focus it down into these tiny, incredibly intense hotspots. These are the zones of extreme energy confinement. This is where they're squeezing reality. So the machine's running. They flip the switch, and the signals that come back are way weirder than anyone could have guessed. This is where the paper starts reporting some truly strange phenomena coming out of those energy hotspots. Let's take a look at what the sensors were actually seeing.
So how do they even read what the NV sensor probe is telling them? Well, they shine a laser on it, and the light that it emits back changes in very, very specific ways, depending on what it's sensing. It's an insanely sensitive measurement. And the signal they picked up? Well, it was not what you'd expect at all.
This was the first really big what is happening moment. The technical term they use is a non-classical phase evolution. But what that means in plain English is this. The sensor started acting as if it was being physically pushed or shaken. But, and you gotta get this, nothing was touching it. There was no physical force. It was sensing a phantom motion. But it gets weirder. The second observation is frankly even more startling. In those exact same energy hotspots, the paper reports, and I'm going to quote this directly, localized deviations in elemental or isotopic signatures. In plain English, in those tiny zones, the very identity of the atoms themselves seems to be changing. Matter itself was acting weird.
Now hold on. Before anyone gets carried away, the paper is extremely careful here. This is not alchemy. They state very clearly that they are not claiming they turned lead into gold. The effect was tiny, it was hyper-localized, and they describe it with the very cautious term anomalous matter state reconfiguration. Think of it as a clue to a much bigger mystery, not the final answer.
So you've got this phantom force, you've got matter behaving strangely. How on earth do you even start to explain that? This is where the paper moves from just reporting data to proposing a very bold new idea. The author puts forward a speculative framework to try and connect these dots, a hypothesis they call the address field. The core idea, straight from the paper, is this. What if the physical world we see is just one layer of reality, built on top of a deeper, informational one? The hypothesis suggests that every particle can be described by its coordinates in an informational state space. And what we see as physical change is really just that particle changing its address in this deeper space. So the address field is basically a model that says reality might have an underlying informational blueprint. The theory goes that the extreme energy from the experiment isn't just shaking atoms around in our 3D world. It's giving them enough of a kick to actually jump from one address to another. And a new address could mean a new location. That's our phantom motion. Or a new address could mean a whole new set of physical properties. That's our strange change in matter. Now look, an idea this huge can start to sound more like philosophy than science, right? But what makes this a really compelling scientific paper is that it brings everything back to what matters most. It has to be testable. A good theory isn't just a cool story. It's a target that you invite every other scientist in the world to try and shoot down. And this is the mark of good science. The author lays out a checklist for how to prove this whole idea wrong. If these effects can be explained by normal, classical physics, it's wrong. If other labs try this and can't get the same results, it's wrong. If the effects don't get stronger when you crank up the power or use a more complex fractal, then the hypothesis is wrong. It's a clear roadmap for the entire scientific community to put these claims to the test. So let's just run through that recipe one last time. You need the structure, which comes from the graphene. You need the drive, from the terahertz waves. And you need the amplification, which you get from that fractal design that focuses all the energy. It's that precise combination that seems to be unlocking these very strange new phenomena. And really, that's what this all boils down to, this one profound final question. This experiment hints that by building these incredibly specific structures at the nanoscale, we might be able to start engineering the vacuum itself. And if we can actually do that, if we can learn to squeeze reality in just the right ways, what else is out there? What new physics is just waiting for us to find?